Good day, everyone. I'd like to start by saying thank you for joining us on this technical topic webinar today. Can everyone please disable their notification by simply going to my settings, the cog symbol in the bottom right-hand corner of the screen. Go to the notification settings and untick all the boxes as depicted on the screen. Thank you, guys. So I'll just wait for a minute for everybody to do the step on the screen and I'll carry on. The technical topic webinar today is fatigue design, verification, and validation of mechanical equipment, which will be presented by Mr. Rob Withers. And he'll carry on with this lovely presentation and walk you through everything. Within the next 2 business days, an email with the link to the video recording and a copy of the PDF slides will be sent out to each participant who registered for the webinar. Please keep an eye on your spam folder. We provide a free digital certificate of attendance for live attendees for technical topic webinars. There will be a link, QR code, to a short form survey provided at the end of the session, which you need to complete in order to receive one of your certificates. Once completed, it will be sent to you within the next 4 business days. A bit about EIT if you are joining our webinar for the first time. We are one of the only institutions in the world specializing in engineering. We currently offer a range of industry-focused courses mainly across civil mechanical, electrical, and industrial automation engineering, from short courses all the way through to a Doctor of Engineering degree. All our courses are offered online and also on campus for certain courses, which means students can study from wherever they are in the world, but also experience studying engineering in Australia if they want to. All our vocational programs, high ed degrees, are recognized and accredited by the Australian government, but we also have a number of courses internationally recognized under one of the 3 international accords: Sydney, Dublin, and Washington. And I'll leave this presentation to Mr. Rob and he'll run you guys through the journey. Thank you, sir.
Okay, so I'll just share my screen and come into my PowerPoint, which hopefully you're seeing now. So Malethi, is that come up okay?
It's perfect. It's perfect. It's on the agenda page, right?
Yep. Okay, that's great.
Yes.
Okay, so thanks everybody for attending and welcome to this session. I hope you'll find it suitably informative and interesting. We've got 11 sessions, 11 sections, 11 case studies, and 83 slides. So it's a bit of a task. The slides and the whole thing has been put together so that it'll be a good summary when you get the PDF. And I believe we'll get through it all, but obviously I'm not going to read every word, and the text in some of the slides we'll flick through. Okay, so in the case studies, obviously numerous details need to remain unstated. So for all the case studies, the comment during the description of "I'm very sorry to have to say" is a given. That is, hindsight's a wonderful thing. Okay, so we'll go through the overall detailed design for improving fatigue design and reducing potential for fatigue cracking, and then design verification with FEA and fatigue, and validation methods mainly on strain gauging. So the output will be those learnings, which we'll get to. The FEA and the correlation will be in accordance with BS 7608, the fatigue code, and the strain gauging is mainly the validation, as I say. So I'd just like to acknowledge at the bottom there the enormous efforts of Barry Morris in leading our instrumentation engineering through hundreds of projects globally for 23 years. And you'll see there the summary of it all, including manufacturing, telemetry, and hardwired strain gauging systems across all industry and equipment types. So the learnings mirror the introductions, and we'll go through design, verification, validation. We'll learn about all the fatigue loadings, low cycle, medium, high cycle, cumulative, rain flow analysis to get cycle and damage histograms. So we'll go through that, and the aim is to come up with obviously a product that functions better, higher quality, higher durability and integrity, less downtime, less repair and maintenance costs, etc. So the context of fatigue is summarised there by ASM, used to be American Society for Metals, where about 20 years ago they reckoned that 90% of all service failures were contributed by fatigue. So 90%. It's probable that in that time it's reduced a bit. It might have reduced to 85, 80, but obviously it's still high. So fatigue design and good verification and validation before you put a whole string of products into service is highly critical. The consequences, again, are obvious. The two on the left we needn't go through. The one on the right is an unfortunate collapse of a reclaimer, where there was an internal weld on all of the outrigger legs, which wasn't able to be visually inspected, and wasn't inspected, and it internally cracked, and the whole weld unzipped, and obviously the outrigger with highly compressive loadings on that top flange right next to the hub, compressive buckled and completely unzipped. So that was very well proven in the simulations. So grinding mills are the classic rotating, bending, fatigue machine. Horizontal mills, and you can see here virtually every component in the drivetrain, as well as in the rotating elements of the trunnions, which the bearings hold, the heads, the shell, obviously all the gearing, the open cut gearing, the pinion, the gearbox itself, the shafting, obviously the discharge trommel screen. Yeah, everything's rotating 15 RPM on your shell, and everything is subject to fatigue potential. So what you need to do, I mean, obviously top left there is major problems. On the bottom is fatigue, and what you've got to do with fatigue is go through every potential hotspot of the trunnions, heads, shells, to work out at your 40% charge, specific gravity around 5, whatever the ore is. So every rev, 15 RPM, you make sure that cycle, stress range cycle, compression to tension, is not creating you a fatigue problem. This is a new shell we designed for an Egyptian site who bought a second-hand mill, which was not in the condition when it got delivered. And the detailing, the weld joint detailing is obvious. So all the shell to flange weld to full penetration, they're all oversized legs so you can fully grind and profile them to reduce the stress concentration. Very high quality welds, highest quality NDT. You must have an excessive leg, so when you fully profile, you don't have too low a weld throat. Obviously, you'll confirm all this with your solid element FE. So this is your typical mill in operation. This is obviously a half longitudinal plane of symmetry mesh, all solid elements, 15 RPM. And that video there is showing the major principal stress. So every cycle, through every cycle, when you go from top dead center where you're in compression, you go to bottom dead center where you're in tension, we open up, and the tension to compression difference there is the stress range as per the strain gauges and the stress derivations. So, you know, that mills 40, 50 mil shell thickness and massive trunnions and heads, there's still a huge fatigue problem because of this rotation and the charge loading as they rotate through the charge and through gravity. So what you've got to do is go through every weld joint, whether it's a full pen butt, full pen T. You won't use fillet welds or lap welds in a mill like this. And look at all the potential fatigue cracking sites, the toe, the root, whatever. Determine what the classification to the 7608 code is. Determine what your fatigue characteristics is, and make sure you're below that. Always obviously using a 2.3% failure situation on your statistics. Your fatigue on laboratory weld specimens is plus or minus 3 on life. So you've got to use that mean minus 2 standard deviation, 2.3% failure, 97.7% success for your design criteria. So this is a bit dated, but some of the early mills had poor manhole cutouts in the shell with the rectangular cutout in the shell for manhole for access, with too tight a radius and a poor outstand fillet welded cover. So this is the manhole cover bolted onto this outstand fillet welded arrangement. So the rectangular cutout with too small a radius exacerbated by the fillet welds, and you've got cracking. You've got cracking at all 4 corners, and that's not done. Obviously, not done anymore. The next step between that was a doubler perimeter type arrangement for your manhole, where you clamp in a cover plate with a doubler, but that's not good enough either. And the best way is to do a full pen insert type manhole cover with good radius, good taper, fully profiled and clamped in, a cover clamped in. So this is a typical flow chart, which, you know, there are hundreds of. The need is to understand and characterize your geometry, your load, your environment, the criteria, materials, and any improvements on materials that you might do. And then you go through your load cases, absolutely critical, your stress and fatigue analysis, cumulative damage, and you get your prediction, and you'll iterate. You'll iterate all through as needed to get to an acceptable result. There's been a lot of studies on cycles for different types of machine. We won't go through all this, obviously, but if you haven't got a good details of your loadings and their cycles, etc., then these type of papers are useful. Offshore structures, automatic transmissions, steel mills, whatever you're after. But you're always best to get your exact loadings for your particular machine, and normally you'll have that. So screens are similar to mills, a classic fatigue nightmare, but worse. They're a reciprocating machine, obviously, on the isolation frame with the spring supports, the body reciprocating back at plus or minus 5G as driven by the eccentric exciters, plus or minus 5G, 600 to 900 RPM, and a very difficult design problem to say the least. So your criteria is less than 2 days, you're up to 2 million cycles at 750. And obviously you've got to do your fatigue design better. You may even use less than 2.3% failure criteria on your fatigue curve. Part 5 is the AS 1554 Part 5 fatigue loading well code. There'll be global equivalents all around. Stress relieving, proper post-well heat treatment, stress relieving for residual stress reductions. The W2A technical note 11 is an excellent summary of the 1554 series. If you can get it, it's got excellent notes. But what you're looking for on the screen is 4 years between maintenance, 98% utilisation, and 12 years total service. So that's tough. So your screen failures will be everywhere. Springs, material feed. Material feed to get right is critical. When you see a coal washery plant with a large lump of coal coming down the conveyor into the feed tube into the screen, the size of a fridge, you know you've got a problem, and it's got to be rectified. Because that's not fatigue, that's overload impact in one foul swoop. Fatigue damage can happen anywhere. Those main drive mech beams and the exciter bolts, your cross beams that hold the longitudinal stringers that hold the deck up, your cleats to hold the stringers, anywhere and everywhere if it's not set up properly. So this is the half stroke. This is just the half stroke of the analysis. Obviously, the other half goes the other way. And what you've got to get the resultant stress ranges from that plus or minus 5G at every location, and they've got to be designed less than your fatigue criteria. You've also got to get your natural frequency modes so that you can get an operating window in that operating range. So you've got your 6 rigid body degrees of freedom of your screen sitting on the springs, 3 translations, 3 rotations. Your first natural frequency on this occasion is your lateral bending. Your second is racking. So the 2 side plates back and forth racking. And your third is torsion. So this torsion is mainly shown by a discharge and twist, but the whole screen is twisting. And you can imagine what all these modes are doing locally to stress ranges, whereas if they're excited. So if you compile a running speed range and overlap those modes in, you should be running at plus or minus 5G. If you excite those resonances or you're on the flank, you're going to be way over 15G, and you're going to crack within hours. So you need an operating window, so you're between resonances and you're not going to have a problem. This is an unfortunate case of a longitudinal stringer where they tried to reduce the height of the top of the stringer above the cross beams and the cleats by tapering the ends here to bolt into the cleats. It's a bridge too far. The weld here, you've gone from parent metal of the channel to a weld, and even though the weld was done well and ground and stress relieved, etc., a bridge too far, just cracking all the way through. So just be careful, finally, of half orders on your screens. If you go too fast, depending on your oar feed, obviously, depending on your deck shape, on your deck flexibility, stiffness, the whole thing. If you go too fast, you can excite half orders, which is obviously going to double your cycles in a unit time. I'd be careful of that. Make sure you're not exciting higher harmonics. This is your typical strain gauge installation back on that stringer. Obviously very intensive to get those gauges there and epoxy covered so that the feed and the process water wouldn't do them away, and your lead wires out to the side of the screen, out to your instrumentation. So the 3 design philosophies, there's too much text on these 2 slides, but basically fail-safe design is if one part fails, the whole structure doesn't fail. That's the first lot. Damage tolerant is a refinement, but it includes regular inspections. Go through that at your leisure. Safe life design is what BS 7608 and most of the fatigue codes are based on. So you're looking for safe life design, so the suitable reliability and durability results, because you're using an upper bound estimate of the fatigue loading. So you're being conservative on the fatigue loading, and you're using a lower bound fatigue endurance data, so you're conservative on that as well. And obviously design for inspection and maintenance. Like that reclaimer, we don't want to design something that can't be inspected. So you've got to have design so you can inspect and keep on top of it. Centrifugal fans are very robust, generally. Power generation, sugar mills, obviously large mine vent and process. Thousands, tens and hundreds of thousands built yearly, globally. Be careful of rotation through gravity and poor startup flow, as well as losing control of wear plates. This is a large double inlet sugar mill fan, which unfortunately lost control of wear plate masses, and also was not controlling it well on the turbine drive. So these things start on a pony drive and switch to a steam turbine, and they had 500 to 700 RPM turbine speed variations. And if you look at that, 500 to 700, that's a fatigue cycle itself. It's causing, obviously, causing an up and down of a fatigue cycle itself. And if you keep on doing that, even twice every minute, you're quickly going to rack up unacceptable cycles. Be careful of wide. The middle here is a typical ratio of your axial width to your diameter impeller. Aerofoil blades, back plate, front plate or cover plate, etc. Your hub's in there, not shown. Be careful of too wide impellers. There have been instances of too wide impellers causing fatigue cracking about the blade noses on the rotation through gravity fatigue cycle. Obviously your RPM loading, your centrifugal loading, is the strength load case. The fatigue load case is caused by rotation through gravity, as well as pressure and flow buffeting. But you must calculate that rotation through gravity fatigue load case. And too narrow, you've got to be careful about disk modes getting excited during startup. So we've had both. This is what I'm saying about rotation through gravity. Ignore the contour plot there. That was inadvertently plotted as a theta. So, hoop stress, theta angle plot, forget about that. The deformed shape shows you that at top dead center, the blade to back plate angle is closing up, so compression. At bottom dead center, it's opening out, so tension. And it's that tension to compression which is making the stress range again under gravity. So, I mean, years ago, people didn't worry about this looking at that fatigue case. It is critical, particularly for wide impellers. And here you've got on a narrow impeller, you've got the disk mode, the first disk mode being excited, and that's an axial contour plot, and it shows that disk mode with the node line of the motion halfway across the impeller. The other main disk mode, lower main disk mode, is the umbrella mode, where the whole impeller fluctuates like an umbrella, opening and closing. Obviously very small displacements, but those need to be not excited as you start up and run down, and for narrow impellers they can be a problem. Okay, so this is another 3 slides with too many text, but the fatigue recommendations are basically you must have easy load paths for load and stress flow, no gross discontinuities, structural continuity, you know, fair and structural continuity of everything into the rest of the structure, welds position at low stress locations. Forget about fillet welds. They've all got to be full penetration T or straight butt welds. The 1554 code, and there's no such thing as a secondary weld. So you've seen truck chassis with don't weld here. That's all that is about. Don't weld on those because you're reducing the fatigue resistance of that parent metal high strength steel by a factor of 5 as soon as you weld a bracket onto it. And it's the same with mine dump truck chassis. Similar things have happened. So that's all fairly obvious, and I hope the case studies will explain that well. Load cases, as I've said before, are critical. The AS 4324 is the mobile equipment for continuous bulk handling code, and it goes through load cases for that equipment extremely thoroughly. And if you can get a copy, or even the earliest version, it'll show all those load cases outlined, and it gets you thinking about what the machine is going to see in service. Okay, the axial fan. This is a return air fan in the most prestigious building in the city in the late 80s. Cast aluminium blades, cracking within weeks of in service across that line there. They were in plan view. They were put in pairs, in pairs, and this pair here was the main culprit of the cracking. Set up with poor inlet flow due to that corner. Somebody thought it'd be a good idea to put silencer pods upstream and downstream of the impeller and motor. Well, that's great for acoustics, but not obviously for flow or stable operation of the fan. Plus, they were variable speed on a variable speed control system, which wasn't tuned very well. So at low speed, narrow band random vibration from those strain gauges. Narrow band meaning one frequency, random meaning obviously random magnitude, but acceptable, still acceptable. If you increase speed, you go from narrow band random to 4 or 5 times magnitude difference, increase, and that's pure resonance. The blade is in pure resonance in cantilever bending. There's not much damping in the whole impeller or blade fits. You can see here the damping after you do an impact test on a blade. It takes a long time to fade away. So there was nothing wrong with the impeller or the blades. but the OEM should have advised the blade cantilever bending natural frequency and ensure no resonance could occur in practice. And I trust if he had seen the drawings of the installation that you would have run alarm bells. So the solution was to remove the silencer pods, add better guide vanes to get around the corner, flow straighten the vanes in the ducting, and a fairing dome on the impeller, as well as fix up the control system of the large speed differences. So here we come to the verification, and this is the meat of it. For solid FE elements, it is straightforward. It should be reasonably straightforward. You'll put your mesh of your weld. You'll simulate that weld. This is elements not shown here, so we can explain something. You'll mesh your hub. You'll mesh your back plate in the inner part with solids, and you'll merge it into shells further out. This is the start of the back plate gusset meshed in shells. But you must make sure that you don't fuse gaps in your solid elements. So this is going back to the mill we saw with the doubler manhole and the welding around inside and outside of that doubler, where that gap, that lack of fusion on that gap is simulated. That's the same here with this backplate shell element. It's not fused and joined into the hub because it won't be. It's only joined into the fillet welds on the back and the fillet welds on the front, so you'll load up your welds properly. So that's critical. But usually if you do a solid element mesh properly, then it's reasonably straightforward, and you'll follow the standard to get your fatigue hotspots. For shells and plates, it's a different matter, and sorry to say that the standards don't seem to do a good job on showing you what a shell and plate mesh should look like. There's all the diagrams showing you what you need to do, but we'll come to the meshing a bit later. What you need to do is find out your stress, 0.4T and 1T out from your weld toe, linearly extrapolate back into that as per here, and there's your hotspot stress. So you're not including the non-linear speak of the knot stress. It's this hotspot stress via this extrapolation method. The joints now normally add is A or B type. So your A or B on the side of the plate, your B will be on the edge of a member. And of course, if you've got a mouse hole or a coping hole or something, you've got to obviously put that in your mesh to get the right magnitude of those locations. The hotspots, I won't go into all this, but the hotspots, as I say, 0.4T and 1T. For hotspot B, there's a different system of this extrapolation. And for coarser meshes, you can do the 0.5T and a 1.5T, but for a coarser mesh. I find this 0.4T, 1T easier and better, but it's up to you. So if you're strain gauging, you'll use a gauge at 0.4T and 1T or 0.6T away from here. And that gauge can't be more than 0.2T long, otherwise it'll average too much over that area. This is from a paper, excellent paper, two papers by 29 and reference 29 and 30. I suggest you get those, easily downloaded. Glinka, it's the 30, done a lot of work. And Glinka here is good enough to show us a mesh, where it's used the inclined shell model. So there's 5 methods to model the weld and the plate with an inclined shell at the center throat distance of the throat thickness, which reference 29 shows here on a double-sided T fillet weld. The third method is increased thickness inside. So these elements here and here are given increased thickness to account for some of the throat thickness. And the fourth method is no weld model, and that was what used to be done back in the day when BS 7608 first came out in '93. That was what you had to do, and the early IIW code of '96. Be careful of that. We'll get onto that. And the fifth method is solids. Obviously solids, but you'll have your gap here. Obviously you have your gap here to account for the root and the fact that you haven't got full pan weld. If you've got a full pan weld, obviously mesh that. But for a T-butt fillet weld, that's got to be meshed. So reference 29 went and worked out the hotspot stress results for 2 load cases. And the results are similar, but that's only for two simple geometries, and Glinka has outlined it better here. So obviously you've got a mid-plane shell element for your this element here, and also on the horizontal plate, mid-plane, give the shell element thickness, and then you need to have an insert weld element as well, or else increase thickness, because that no weld simulation is not good enough to look at hollow tubular section joints or more complex joints than a simple laboratory joint. You can do this yourself, like I've done. Set up a solid mesh with the gap in there, as you see, or your added thickness mesh, or your insert inclined mesh. This is showing the plates with thickness on them. This is showing the plates with just the membrane with no thickness plotted. And if you do the bricks, you'll get that plot into the weld tone. 0 is the weld tone, always into the weld tone. And that plot is what you've seen before in the code. Increases, stress increase into the weld, and there's your extrapolation. So that's all there is to it. So as I say before, you look at your class of your joint, and you'll compare it to the hotspot stress to the D line of the fatigue curves. And from 93 to 2014, when the latest 7608 came out, there was a heap of work to sort this out, to sort out which class of fatigue line was to be used for hotspot stress. And the IIW codes came to a similar conclusion. So you've got those results, you've got all your cycles, you do your rain flow counting. This is to the ASTM E1049 standard, your rain flow counting on your variable cycle loading. What you're doing is you're counting half cycles and putting them together to get the cycle numbers. You put that rain flow into your fatigue summation, your Palmer-Miners rule, where you're looking at the ratio of the number of cycles to the allowable number of cycles at that stress range. And you'll come up with a damage histogram and your fatigue damage, and your life is 1 over D, 1 over your damage. So if you've got here, this is 0.045, so 1 over D is 20. So if that's your cycle in a year, you've got 20-year life. Obviously it's not for this case, but that's your cycles over that time, then the life is 1 over D. Okay, to wrap that up then, read the standard fully. don't use the no-weld mesh. If you want to use that to initially do your, I mean, if you're going to model a ship structure, you're not going to model it in solids. You haven't got time or disk capacity. If you want to do that mesh initially, okay, then finish it off with the additional thickness mesh method and/or the inclined shell mesh. But for, you know, for a stereo fan, for a vibrating screen, I wouldn't use the no-weld mesh. I'd use straight into additional thickness or straight into inclined shell mesh. There are corrections on the 7608 curves for thickness and bending and temperature and seawater. Tubular node joints are managed slightly differently, and the weld toe improvement need to be used if you're using that in a couple of slides. I mean, you've got to be careful about weld toe improvements, because if it takes you a lot of time and effort and cost, then you're better off using a bit thicker plate and larger welds to get your fatigue resistance down. I'd suggest you do your bolt fatigue to the German VDI 2230. M Design is a German company that has software to that. Very intensive standard, but for whatever reason, the 7608 doesn't handle bolt fatigue up to date enough. Mean stress effects we know about, Goodman, Morrow, etc. for parent material. There's an excellent summary in the Siemens community there. For weld root fatigue, look at references 33, 34. You've got to avoid that because you won't obviously you'll find it with radiography and UT, ultrasonic NDT, but you won't find it visually. And then stress relieving. TWI do a lot of good knowledge links with stress relieving, the benefits and the reasons. So higher end FE verifications, the explicit solvers, you can look at a drag line where inadvertently the truss of the boom has become broken, and that's going to cause you a buckling problem if you don't fix that soon enough. And obviously the other typical explicit solver is the crash and impacts, where you've got to have a minimum deformation for a 50K crash for your tender, your design situation. Okay, the post-weld fatigue improvements we talked about. Good summary there. I'll leave it with you. The residual stress, your peening and high frequency mechanical impacting, etc. For thermal, you're thermally stress relieving. For weld geometry methods, your machining or your TIG remelting or whatever, please don't use disc grinding. Disc grinding will leave you where your marks are always going to be parallel with the weld. Your line of your disc is parallel to the weld, so your marks and grooves are parallel to the weld, which is terrible for your stresses, which are mainly perpendicular to the weld line. So please don't do that. If you want to do that for very rough weld material, do it. Make sure you've got no grinding marks left, and you finish off with a burr grind. Okay, this is another rotating bending case with a chill roll in a plastics laminating plant. This was imported from Europe to a Sydney plant back in the late 80s. So the chill roll is that one there, which laminates plastic out of here, hot plastic onto the cardboard paper as it goes through, rotating, and it's compressed. It's compressed, obviously, to compress the plastic onto the cardboard about the chill roll with the pressure roll. So that situation of rotating and lateral loading is a high bending moment from your bearing to that stub shaft connection to the outer roll, and it's screaming rotating bending fatigue. And for some reason, this was designed with 3 gussets, only 3 gussets between the chill roll and the stub roll. Plate, circular plate in here to end it off. But as soon as you see that, you know this is a problem. The high bending moment right there at that cross section is going to tear this weld joint here on the inner edge of these gussets, and it did within a matter of weeks, and you've got a problem. So this thing was designed with no thought to fatigue, I'm sorry to say, not only in that overall concept of the 3 gussets, but also in the poor fillet welding, etc. So we sorted that out, obviously, with gauges and telemetry, and looked at different rectifications with discs and stub shafts, with discs and continuous stub shaft, higher ratio aspects, but they obviously would stop you getting access to your water hoses and connection coming in and out. And the best solution obviously was 6. So very basic, 6 gussets, increased thickness at inner and outer edges, full pen, oversized welds, fully profiled, similar to this joint, which is on a Singapore bridge. So, I mean, this joint here is aesthetics as well as structural. But where needed, you know, on a low production item like this, you can beneficially use full profiling on oversized welds and stress relief. This is a couple of ships. We're running out of time, so I'll have to miss the truck load case, but ships. This is a brilliant self-unloader from Catherine Hill Bay to Port Hunter in the early 90s. It was cracking across the ballast tank. The ballast tanks are in the cargo, 2 cargo holds for the coaler here. Ballast tanks are on the side, and they obviously have a closed end panel as well as open, you know, 4 or 5 open frames, and it was cracking at these lower longitudinal hull side stiffeners as well as further up on both sides. And the reason for that was the shear. Once per day shear loading, coal full and unload. This is the shear change through the beam of the vessel, and that shear was creating a shear buckling of the sides of the frame, which needed a cross tie, and that cross tie was added very well in Newcastle. The second ship was a large tanker back in the early 90s, cracking on a ballast tank frame, a panel, a lower panel, which still an open frame higher up, you'll see, cracking across the longitudinals to the gussets, longitudinals going across the cross stiffeners to the frame. 5-cylinder direct drive diesel, and we thought that was similar buckling, low cycle buckling, due to the change in load and unload. That was wrong. It was the 5-cylinder. If you look at the ballast tanks, this is the cracking here, and in the frames above had the cross ties, one cross tie. That's great, but this large panel here wasn't happy, and the 5-cylinder was way too high in vibratory torque, up near maximum continuous running. So normally you have a vibratory torque peak, which peaks down here and then reduces, and you'll have a bar speed range down there, and you'll have your operating speed higher up. For some reason, this was put in, and nobody looked at this high vibratory torque at common running speed, and so your prop is going around and thrusting, but it's also vibratory, got vibratory motion on it because of the vibratory torque, and it's going back and forth and causing the axial thrust, vibratory thrust. So it's not just mean thrust, it's vibratory because of the torsional vibration. And that was shown as soon as the ballast tanks were full, they went from very low strain to through the roof. And if you look at dynamic stress to speed, it's through the roof with tank level. And that was rectified in Singapore with a stiffening, good gusseting and stiffening as should have been designed initially. So this is a dump truck. We don't have time for it. I'll leave you to go through that.
G'day, Rob. Sorry for jumping in abruptly. It's Riley here. I was just suggesting we've got another 10 minutes until the webinar's scheduled to end. So feel free to do the next case study if you would like to.
Oh, that's good. Oh, thanks, Riley. That's good. Yeah, I mean, I don't like to rush these things, and this is an important study, so that's great. Thanks. So this is a dump truck tray in the early 2000s up in one of the Queensland open cut mines. Nothing to do with the truck manufacturer. The trays were subcontracted to a tray builder, and obviously you're trying to save weight, but you've got to make sure you don't overdo it. And unfortunately, it was overdone, and the design of the laterals and the longitudinals, the canopy, the elephant ears, the rear unsupported, it was just not thought of. You'd almost imagine there's three teams involved here, one designing the tray, one designing the laterals, and one the longitudinals. And obviously that's not the case, but you see what I mean. And unfortunately, the cracking there was horrific. So, I mean, you've got operations with shovels. The shovel operations weren't flash. The haul roads from the fill to the dump weren't good. So, you've got impacts from loading and uneven loading. You've got higher than should be accelerations, and you've got an unfortunately weak design, and that's the result. So that was all gone through with looking at the load cases. Again, load cases. So 12 load cases set up, including your tail dragging of your dump, the loading, etc., your lateral accelerations, rolling and lateral. And that was all set up and properly sorted out through your FE. And you can see there the modified body, you've got your tail fully supported into your longitudinals. You've got your laterals all the way up to the top of the tray. You've got more ribs on the canopy. You've got better elephant ear detailing with a flange. And the whole lot is structural continuity. There's no gaps or no hot spots or load paths which stop. You've got structural continuity and fairing flanges and web gussets, etc. And that worked very well to be rectified on a prototype, one of the prototypes, and then it went through the whole fleet. So that was a good result. And at the same time, the shovel operators we had a team meeting with them, and the roads were improved, and it was a good result. So just for awareness, stress life we've been talking about, and stress life is the fatigue I've done, but strain life is low cycle, high strain, and strain life looks at elastic strain and plastic strain and then total strain, depending on your cycles, and it's parent material, and be aware of strain life. There are plenty of codes, obviously, that do the stress life as well as strain life. This is a strain life, low cycle situation of the lifting lugs of this army barge, army watercraft, sorry. Obviously, the cycle of lifting and lowering and down and coming up is low cycle. Please don't just plonk a lifting lug tab on the side deck, fill it welded, and then put a couple of gussets there to help with lateral loading. The cracking was obviously immediate at these joints, and that was rectified with a haunch, a proper haunch type of lifting lug fed into the rest of the framing structure with a rud link, a pin and a rud link to do the job. And that's how it should have been done in the first place. So multi-axial fatigue is again awareness. Again, the fatigue of all that previous is been uniaxial fatigue, where one direction stress range is highest. The case that has obviously the multi-axial is the ball mill with that square manhole at 90 degrees, so it's at the side. It'll be under shear at the corners, and then when you get down to the bottom, you'll be under normal stresses at the bottom, and that's the typical situation with your non-proportional loading 90 degrees out, your shear 90 degrees out from your normal. And ships are in the same boat. So, I mean, multi-axial fatigue work commenced in the 30s. And since the last 30 years, they've been absolutely intense and work and hundreds of papers written, and it's still going. It is still ongoing, and it's not certain when it'll finish. It'll probably never finish. But to cut it short, to close it out, the IIW codes recommend a damage ratio of 1, which is your normal damage ratio. But for non-proportional, they go down to a damage ratio of 0.5 and even less. And BS 768 has the same conclusion, but it's not well written it's only in text. It's not well compiled, unfortunately. But that's the guts of it. This paper here has looked at, reference 12, looked at 17 multi-axial algorithms and compared them all and shown their positives and negatives. And the author obviously tells us his is the best. It possibly is. But to conclude it, if you got a multi-axial fatigue situation, get a suitably qualified and experienced consultant who's got one of the software codes that handles it. You're not going to write your own algorithm. You're not going to know which one to use. Well, I shouldn't say what you're going to do and what you're not going to do, but you must use one of these. Otherwise, you'll have no certification at filling your results. Okay, validation. We've gone through validation with the strain gauging, etc. It's not factory acceptance testing. Factory acceptance testing is running through a few normal load cases. Validation is going through the whole, like the 4324, the whole load cases you expect and get your results from that and correlate them with FE and fatigue analysis. Obviously, strain gauges and the like, there's plenty of sellers and they have got excellent technical manuals. Time, you need time to set up. You need cooperation and collaboration with your operating site. If you don't, you might as well not start. So obviously on site it's different too if you've got a dedicated lab for bogey testing, as in the States, or the wind turbine blade testing, as in the States or in Germany. So obviously these dedicated labs, you haven't got a production manager screaming at you for losing production and sending you broke. But yeah, it's a different story. You've still got to work efficiently. Okay, the final is this tubular agitator, 20 to 50 RPM tubular agitator in a processing plant. Helical tubes welded to lateral arms for water cooling. An absolutely intense setup of telemetry and strain gauges. The outer arms, helical arms on the lateral arms, they repaired 5 welds over 2 weeks, all more and more intensive welding and profiling and the whole thing with no result. So obviously the troubleshooting was needed, and what it was a huge increase in your alternating strains at 41 RPM. Low revs, great. 41 went through the roof, and that was vortex shedding, exciting the 5th mode. So this thing again has no damping. That's the 5th mode excited by vortex shedding at that 41 RPM, and there's nothing, there's no weld, perfect weld. You just can't handle that. So the solution obviously was just to, very basic solution, put vertical tubes, clamp vertical tubes in there, clamp them so you didn't make a stress hotspot with themselves, and that knocked out that mode. Okay, so thanks for that. I apologise for running a minute over time, but hopefully that's been of interest and use. And I guess if there's any chat, if there's any easy questions, we can answer them. So I've got to unshare. Okay. So Riley, Maleffi, you there?
Yes, Mr. Rob.
Okay, I understand you're going to finish it off, please.
Yeah.
76 chat messages. Whoa.
Upcoming courses. We have a range of courses in civil, electrical, mechanical, and industrial automation engineering. To see our full course schedule, please kindly go to the link in the chat box, which I'll put right away. And on that link, you can go to our website and see our upcoming courses. Upcoming webinars. Don't miss out on our upcoming webinars. And I'll put the link also in the chat box if you're interested in the upcoming webinars, which will be exciting also. So please follow the link that I put in the chat box, and you'll see a whole list of our upcoming webinars. Certificate of Attendancy. To receive your digital certificate of attendancy for participating in this webinar, please fill out the form and survey. I'll put the link in the chat box also for you to fill in the form so that you can receive your certificate of attendancy. Or you can scan the QR code and fill in the form. So I'll leave this for just a minute so that everybody can see everything that's going on the screen and can fill in the form. So Mr. Rob, I'll leave everybody to ask their questions now, and please answer all the questions that are directed to you. So if anybody has questions for Mr. Rob, please do
before
ask
you
him
do
now.
that, before you do that, the list of the chat questions, we've got those recorded, haven't we?
Sorry?
The list of chat messages, we've got those recorded.
No, we
How do we
don't.
save those? How do we save those for future?
I have to read out the questions, then from there you answer the questions. And that's how.
Okay.
If I can just jump in quickly, we've got the chat box that is recorded as well. But if everyone can put their questions in now, you should be able to see a couple questions there now, Rob. There's a couple of technical questions that have just come in.
Okay.
So Moiketsi Mukwena just asked a question. Do FEA load cases cover all angles in as far as preventing fatigue load effects is concerned? Or do some load cases emerge in operations without a possibility of prior prediction? So that's a question from Moiketsi Mukwena.
Yeah, that's a good question. For sure, it depends. That 40 years ago, that was certainly more prevalent than now, and for unusual machines, yeah, and for screens, for difficult material handling, stacker reclaimers, the machines that slew and luff and the whole and telescope of the whole like for sure. But that's reduced somewhat now, and you should be able to get your FE load cases pretty well complete to be able to cover all your operational load cases. But there's certainly still that potential, so you've got to keep an eye out for it in commissioning and early operation.
Then
Yep.
Mr. Jerome also just asked a question. Does a change of material design affect the fatigue analysis?
Oh, for sure, for sure. The fatigue we've been talking about there is for carbon steels in the yield as per the code in the yield range 200 megapascals up to 960 megapascals. So carbon steel of the different strengths. That's what the 7608 covers. Obviously, if you're going to use aluminium, then you've got about a third of the allowable fatigue stresses, and the aluminium codes detail that, etc. So for sure, the material and the fatigue curve have got to match exactly.
Sorry if I pronounce anybody's name. Akim asked a question also, which is more durable to fatigue between ball mill and vertical mill design?
Well, both have their issues. The vertical mill, yeah, the vertical mill has come in more recently, and it possibly has lower fatigue stress ranges on it. I mean, there's still the fatigue stress ranges involved in it, but you haven't got the same rotating bending through the charge and gravity as you have in a horizontal mill. So there are differences, but you've got to make sure you sort them out with suitable FE. Yeah.
Okay, then be back. Sorry if I pronounce your name wrong. I'm sorry. Did any analysis of nitinol for the propagation of crack, but I was unable to do practical, so wait, sorry. It just moved out. How can I validate it?
If you're talking about crack propagation, then you're getting into fracture mechanics, which I won't go into, and I specifically didn't go into fracture mechanics or knot stresses. And that's metallurgy. For sure, if you're going to have crack propagation, if you want to predict crack propagation, then you've got to do intensive fracture mechanics analysis, and you've got to do it right. But be aware that fracture mechanics laboratory tests, they haven't got a scatter of ±3 on life as a weld fatigue laboratory test has. They've got a scatter of ±10. So I've not gone into fracture mechanics because I've looked at it saying, well, if you've got fatigue crack the rule of thumb is your fatigue crack will go into your microscopy, and you're starting your fatigue crack for 90% of its life, and that crack will take 10% under the same loading to propagate and fracture. Okay, so if you've only got 10% left, you've got a fatigue crack already. The way I see it is you've got to stop the machine and fix it. If you sit around and try to do some fracture mechanics theory to try and predict when in that 10% you've got to press the emergency stop, then you may have a problem.
Brian also is asking, sorry.
Sorry, I'm aware fracture mechanics is obviously extensively used in industry. I'm just nervous of it.
Brian is asking, are there any available software aside strain gauging to determine failures relating to fatigue?
The fatigue, yeah, the three software, I'm not sure of the question, but the three software programs I outlined, FE Safe, CAE Fatigue, and Design Life, they're three of the main ones. There's numerous others, but those codes work with FE and then the uniaxial, biaxial, multi-axial fatigue to give you your fatigue prediction. If that was the question.
Then Moiketsi Mukwena, can we consider wind loads of structures placed outside as fatigue loads?
Sorry, can you say that again?
Can you consider wind loads of structures placed outside as fatigue loads?
No. Wind loads must be included in your fatigue analysis. Absolutely. As must thermal loads and thermal restraints causing thermal fatigue. Pressure loads, obviously in pressure vessels. Pressure load cases causing fatigue. Wind loads on your wind turbine blades are obviously the critical aspect, which is why the huge laboratory when wind turbine blades are set up. Absolutely, wind loads must be included.
Vivek is asking, what software do you use to simulate fatigue? Are there any specific for it?
We've done intensive Excel files on the fatigue curve. We've done rainflow software to the ASTM E1049. We've then done the cycles versus stress range plots, and then gone into the damage summations, and that works very well. It's obviously falling out of common use now because the dedicated software codes do all that for you, depending what you need. But I mean, these codes are not cheap. But I mean, it's not cheap if you have a problem with a machine either. So you've got to weigh it up.
Okay, I think those are all the questions for now. And if anybody still has questions, I'll put our email where you can get to us and ask any questions that you would like for us to answer, and we'll get back to you. And the email address is there. So I just put the email address in the chat box for anybody that has questions. And yes, we will be sharing the presentation to everybody that attended the presentation. So yes. Thank you very much, Mr. Rob, for that presentation. It was
Oh, thank
lovely.
you.
It was very informative, and I'm guessing that everybody enjoyed it from the looks of the chat box. I can see that everybody really did enjoy it, and the questions were also very exciting from the audience. Thank you very much, Mr. Rob, and for our
Thank you.
contact details. Sorry.
Thanks, EIG, and thanks to everybody for attending. It's, yeah, I appreciate the questions. They're good questions.
And thank you very much, everybody, for attending this technical topic. If you still have any questions, as I said, please go to the email address and send your questions there. And for our contact details, if you can go on the screen right now, you'll see all our contact details, and you shall get to us in any form that you want on the screen provided. And thank you very much again, Mr. Rao, for that presentation. I could never thank you enough because it was very nice and very informative. Thank you.
I appreciate it. Thanks very much, Riley. Thanks, Riley, for all your help.